3.2, we're going to look at the least squares regression line. You may have heard this in other classes described as the line of best fit. All right, so regression lines, we're only going to do linear, so straight line relationships. And so if we think one variable can help explain the relationship with the other, then we can come up with a regression line. Okay, in statistics, we use this form for regression lines. So it's y hat equals a plus bx. Okay, and y hat is a predicted number. And we have to make sure we use that word predicted. So y hat is the predicted value for a given x value. All right, so here we have some data for a Ford F-150, all right, and how the price changes with the number of miles that are driven. Okay, sometimes you will see it written instead of y hat and x, they will actually use like descriptions of the variable. So like price hat, because price is the response variable, and then miles driven is the explanatory variable. So if we want to predict the price of a Ford F-150 that's been driven 100,000 miles, that means we're plugging 100,000 miles into that miles driven or x value. Okay, and then we do the math, and so our predicted price is $21,967. Okay, now can we predict the price with 300,000 miles driven? All right, if we look at this data that we have, everything seems to be, we have, I think 8,000 is the smallest, and then about 144,000 is the largest. So we can, let's use our equation. All right, if we put 300,000 in for miles driven, we get negative 10,613. Okay, that number doesn't really make sense. No one's going to pay us $10,000 to take their truck that has 300,000 miles driven. Okay, when we are using X values that are far beyond our collected data, either a lot smaller or a lot bigger, we call that extrapolation. Okay, a lot of times that is not accurate because things change. Like once we get over a certain amount of miles driven, the value of the truck might not follow that same pattern. So we want to be careful that we're not using those predictions, or that we note that those predictions may be off because our data is far outside of what we have collected. Okay. A residual, okay? So when we draw these regression lines, they're not going to go through every single point in a scatter plot, which means that some of them are going to be a little bit higher, some of them are going to be a little bit lower. That distance, that leftover, we call that a residual, okay? So here's like all the different points, our data points that we collected. This is the line that fits them the best. Okay, and so the distance between the actual data point and the prediction from the equation, that's called the residual. Okay, the way that we find residuals is the actual value minus the predicted value, or y minus y hat. Okay, actual value minus predicted value. All right, so we go back to our truck. Let's say that we have a truck that was driven 70,583 miles, and we want to know what the residual is for that truck. Okay, first thing we need to do is find the predicted price. Right, so we're plugging that into our equation, and we get 26,759. Now, in our actual data, the price of that truck was 21,994. That came from this data point right here. So to find my residual, it's the actual price of 21,994 minus the predicted price. All right, and so we get negative 4,765. That is the residual. Okay, and we want to interpret that residual. So like everything else, we have a sentence. Okay, the actual, whatever your y context is, and then we have to say above or below. So we're always going to report the residual as a positive number, and then we're just going to indicate direction by saying it was above or below. Okay, so for our truck, the actual price of the truck was $4,765 below the cost predicted by the regression line. So it would be incorrect to say it was negative 47.65 below. Okay, so in your interpretation, always write this number, the residual, as a positive and indicate direction with the word either above or below. Then we got to be able to interpret some pieces of our regression line. Okay, so make sure we understand A is the y-intercept and B is the slope. And we should be able to interpret both of those numbers in the context of the regression relationship that we are looking at. Okay, so We'll go back to our Ford F-150 example again. Okay. Again, sentences. Okay. For slope, the predicted y value either increases or decreases by whatever the slope is for each additional x context. So, the slope is a unit of change. Remember, we learned this all the way back in Algebra 1, okay? So the predicted heart rate increases by 4.3 beats per minute for each minute, okay? So whatever this, this should be your explanatory or response variable and explanatory variable, okay? And then for the y-intercept, that is what it is predicted to be when x is 0, okay? And we're always going to put that in context. So let's look at that with our truck, okay? The slope is negative 0.1629, okay? So that means that the predicted price of a used Ford F-150 decreases, because my slope is negative, by 0.1629. It's okay if you don't put this cents number, for each additional mile, because mile is my x context, that the truck has been driven. All right, then when we talk about y-intercept, okay, the predicted price in dollars of a used Ford F-150 that's been driven 0 miles. One thing about the y-intercept is it may or may not be meaningful. In this case, getting a used truck that has 0 miles, probably not possible. It could be very close. All right, so we have to make sure that our y-intercept makes sense. So if it doesn't make sense for the x to equal 0, then there's no reason to interpret the y-intercept because it's not a meaningful value. All right. The other thing is we want to make sure that we are using the word predicted or something that means the same as predicted anytime you're talking about y, okay, because we are using a regression line, so those y values that we're talking about are predicted y values, not actual y values. So make sure you use that word in your interpretation. Okay. The model that we use in AP Stats for getting regression line is called a least squares regression line. Basically what that means is if we take each of the residuals and square them, we're trying to draw a line so that the sum of these squares is as small as possible. Okay, again, you're not going to be asked to do the math on this, but just kind of understanding that that's the model that we're using to try and come up with this equation. All right, so we want the sum of the squared residuals to be as small as possible. But typically we are going to use a calculator, or it's going to be given to you using software. Okay, there is one way that you may be asked to find the regression line, and that is using these two formulas that are on your formula sheet, where the slope is the correlation R times the standard deviation of all the y variables divided by the standard deviation of all of the x data. All right, then you would take that b and plug it into this equation, a equals y bar, that means the mean of all the y values, minus b, which we just would have found, times x bar, which is the mean of all of the x values, okay? And in this situation, those values that you need, sy, sx, r, the averages, they would be given to you in the question, okay? So we'll look at an example here. They tell you x bar is this, sx is that, they give you y bar and sy, and then they give you the r. So basically at that point, we're just plugging in numbers, okay? So here's my equation for slope. I plug in the given values, and I get a slope of negative 0.422. All right, then I take that slope value and plug it into my equation for a. That gives me the y-intercept. And then the last step is I'm going to write that equation with the format that we learned earlier, which is y hat equals a plus or minus bx. Okay, so we're just plugging in the a and b that we found. And then anytime you're writing an equation like this, we want to make sure that we define our two variables. So what is y hat and what is x? Okay, and remember, y is always going to be predicted. So in this case, y hat would be the predicted math score, and x would be the percent of students on free reduced lunch. Okay, so again, those values would be given to you, and at that point, it's just plug and chug. All right. If determining whether or not a linear model is appropriate, remember that these regression lines only work if our data have a straight line pattern. Okay. So to do that, we're going to look at something called a residual plot, which is just a scatter plot of all the residuals. All right. Something that you are not going to be asked to make is going to be given to you. Okay. When we look at a residual plot, we're looking for no pattern. We want it to look completely random. If it looks completely random, that's good. A linear model is good. If it looks like it has a pattern to it, usually it's a curve, that's bad, and that means a linear model is not the best way to describe the data that we are looking at. Okay? So these two clear patterns, those dots form a curve, these dots form a curve. That means a linear model would not be good for this data. All right? Here's our trucks. See how those are kind of random? I can't really draw a line between them that would form a pattern. So that means the linear model is appropriate because there's no pattern in the residual plot. There's also some numbers that we can look at to figure out exactly how well the line fits the data. Okay. There's two things that we look at. We look at the standard deviation of the residuals, which is S. Okay, and that is measuring like the typical size of a residual. So it's kind of telling us like how far are our predicted values away from the actual values on average, right? Again, here's a formula, not something you're going to be asked to calculate, okay? You're going to be asked to interpret it, but not calculate it. Okay, and then same thing with R squared. R squared is called the coefficient of determination, okay? The best way I can describe this to you is it measures the percent of variability in the Y value that can be accounted for by whatever X value we are using. All right, and I'll give you a sentence, but we'll talk about this in an example because I think it's a little bit easier to understand. Okay, so we'll go back to our truck data. Okay, we have an equation, and then technology gives us S and R squared, and so we want to interpret those two values. Okay, so here's your sentences. Standard deviation of residuals, it looks very similar to our other standard deviation interpretation. So the actual Y context is typically about whatever S is away from the predicted value. LSRL is an abbreviation for least squares regression line. And then for coefficient of determination, about R% of the variation in Y can be explained by the linear relationship with X, right? And you do have to include that word linear relationship because that's the only time R is valid. Okay, so if we look at our truck, okay, the actual price of a Ford 150 is typically about $57.40 away from the price predicted by the least squares regression line. Okay, and then for R squared, about 66% of the variability in price is accounted for by the relationship with miles driven. Okay, so a way to think about R squared. The price of a used truck, the number of miles on it is going to be a big factor in how much that truck is going to cost, but it's not going to be the only factor. Okay, it could be lots of other things like, has it been in an accident? What kind of special features does it have? Does it have an added stereo system or upgrades done to it? Have things been replaced by the previous owner? Okay, so what we're saying is miles driven accounts for about 66% of the price. And then all of those other things make up the other 34% that changes the price. Okay, for a lot of these questions, they will give you a computer output that looks something like this. They vary slightly from form to form, but generally it looks something like this. And from this computer output, you need to be able to identify the slope, the y-intercept, the standard deviation of the residuals, the coefficient of determination, and the correlation. Okay, so let's talk about where we can find these things. Constant is your y-intercept. Okay, this one says X. Sometimes this might have the actual variable. So like for our truck, instead of X, it might say miles driven. Okay, and then that's where you're going to get your slope. Okay, so constant is y-intercept. X, or name of variable, is slope. Okay, S is S. That one's really straightforward. All right, R squared is R squared. Sometimes they don't list R separately, but R is the square root of R squared. So if they just give you R squared, we can take the square root of that, and that would tell me what R is. Okay, so you want to make sure you can read these computer outputs and find each of these 5 things. All right. So here we'll give you an example. Okay, we got a scatter plot with a regression line, and then this is our residual plot. Okay. So would a linear model be a good fit for this data based on our residual plot? Okay, and then here is a computer output. All right. Can you find those 5 things? So slope, y-intercept, S, R squared, and R.